Hello everyone and welcome on today's video. My name is Wouter Pere. I'm the founder and main developer behind GHEtool Cloud, and in today's video we'll be talking again about hybrid systems. It's the second part in a three-part video series where we will discuss the advantages of hybrid systems and how you can design geothermal hybrid systems with GHEtool Cloud. So if you have not watched the first part, please go ahead and do so. It's linked in the description. But just as a brief recap, in the first part we discussed what are hybrid systems. So hybrid systems is basically a term for any combination of multiple technologies. So in the case of geothermal hybrid systems, it's always a ground source heat pump, but in combination with an air source heat pump or with solar thermal collectors, or with, for example, an air source heat pump and a dry cooler. And we have said that hybrid systems are beneficial because they're good for the investment cost, because by spreading your required power to heat and cool your building across multiple technologies, you can also leverage the benefits of those different technologies. And for example, some technologies might have a lower investment cost since the borefield is rather expensive. And that's why hybrid systems can be good for the investment cost of bigger systems. And it's also good for reliability because you're not focusing on one technology alone. And since you have different technologies, if one of them fails, you still have other technologies to heat and cool your building. So that was the first thing we discussed last week. Another part we talked about was the concept of geothermal potential. Now, as a recap, what was geothermal potential? I made a distinction between three types. So we first said, well, there is a concept like geothermal potential for power, which is, for example, the case in the figure below, where we see that the temperature profile or this borefield is limited in the first year of operation, but it does not reach the minimum fluid temperature in the last year. And this means that we can still add some extra power to our ground source heat pump because we do not reach this minimum temperature. So we can extract more power from the ground. So that's why we say, well, this borefield has potential for power. When we do so, we can end up with a figure like this, where we are board limited in the first year of operation and the last year of operation. And that's why we say, well, we cannot install any more power onto this borefield, because if we do, then we would cross either the maximum or the minimum temperature fluid limit. But, as you can see, in the last years of operation, there is still a lot of potential for cooling. And in the first years, we can still extract some more heat from the ground. So imagine if we would install some extra power onto this borefield. We could extract more heat in the first years or provide more cooling in the last year of operation, so we can exchange more energy with the ground. But looking at it from a power perspective, we cannot have more peak power since we're already limited by the temperature limits there. So that's why we say this borefield has no potential for power, but there is still potential to exchange energy with the ground. And that's when we end up with the third situation, when there is no geothermal potential at all. As you can see, we now reach the temperature limits in every year of operation. So in the first until the last year, on both the maximum and the minimum fluid temperature limit. So we cannot install more power or extract more energy from the ground, since that would cross the temperature limits. And that's why we say, well, if we end up in this case with this borefield design, then we have no geothermal potential left, and we have used our bore field to the fullest. So if we then circle back to our question of hybrid systems, we discussed that in order to design a geothermal hybrid system, the main question was, well, what percentage of my building loads, what share can I get with my bore field? And it really depends on how you design the bore fields. Do you design the bore field so there is still some potential left for energy? Or do you design it in such a way that there is no potential left? And we discussed that this is a design choice which has a difference in capex and opex, in investment cost or in operational expenses. So in today's video we will be focusing on the design methods themselves. So we will discuss two methodologies that are implemented into GHEtool and that will give us an answer to how you can design a bore field so that it's optimized for power, but it still leaves us with a bore field which has potential for energy, or how we can design a system that's optimized for energy and that gives us a bore field with no remaining geothermal potential. And in the third part, we will see how you can design your hybrid geothermal systems in practice using GHEtool Cloud and these methodologies. So today it's a more theoretical part, but it's important to understand how such an optimization works in order to really understand the results you're gonna end up with in the end. So let's get started. First, if we want to optimize our bore field for power, we have a certain objective. And the objective is that we want to maximize the power that we can inject in or extract from the ground at all times. And that last part is really important, the at all times, because this means that if we install a certain amount of power for heating, we know that we can, during the whole simulation period, be sure that we can get that X kilowatts of heating from the ground. And this is exactly the case when we have a bore field that has no potential for power, when we reach both the minimum and the maximum fluid temperatures. Because in this case, if we would install, let's say, 10 kilowatts of heating power extra, we can use it in the first years, but in the end we cannot use that extra power. So since we want to end up with the maximum amount of power that we can use each year of the simulation period, we cannot install any more power in this system. So how do you end up with a bore field that is designed like this? Well, this is kind of the flow chart you can follow. So what you do is you start with a low duration curve and a certain fixed bore field size. Now, these methods and also the optimize for energy, it really requires hourly data because we're going to play with peak powers and energy, and you need a high resolution in order to be able to do so. So you need a dynamic simulation for your building, or you need to come up with an hourly demand profile of the building you want to optimize for. And you also want to have a fixed bore field size. Now, it does not really matter how you come up with this fixed size. For example, it can be that you have only limited space and it's the maximum size you can drill in this space, or perhaps you have a limited budget, or perhaps you're playing around and see where the economic benefits and related to the investment costs. But the most important thing for this methodology is that you start with hourly load data and a bore field of a particular size. And what you do then is you calculate the temperature profile with the hourly data, and you're going to check in step 3 if the temperature limits are crossed, basically. So when we say, well, if the average fluid temperature crosses the maximum temperature limitation, then we can say, well, there is a problem with cooling. And if there is a problem with cooling, then we need to decrease the cooling load by X%. And if the temperature limitation for cooling is not crossed, then it's perfect. Then we need to don't need to do anything. If we cross the minimum fluid temperature limitation, this means that we have too high a heating peak onto the borefield, because we extract so much power from the ground that we go below this threshold. So if that's the case, what we need to do is we need to extract less heat from the ground, so we need to limit our peak power again by a certain amount, a certain percentage. So we do these checks, and then we go to step 4, where we see, well, is the minimum and the maximum fluid temperature within the limits? If it is, then we're done. Then our total borefield is sized in such a way that we can always deliver our installed heating and cooling power. But if it's not, then we go to step 5 and we recalculate the hourly load for the borefield, but now taking into account the maximum peak heating and cooling we've set in step 3. And then we recalculate the hourly temperature profile, and we again check if the temperature limits are crossed. And if they are, then we again decrease the peak power we put onto the ground, and we iterate until we see that the total temperature profile stays within the temperature limitations. And then we're done. So imagine you have a system with 536 kilowatts in heating and 670 kilowatts in cooling. And for one reason or another, we only have 80 boreholes. Perhaps it's for budget reasons. So if we run this optimization, we can end up with a figure below. So we have the load duration curve of the building, and the hedged area is the share the geothermal borefield can play when we optimize for power. So when we do the optimization of the previous slide, we know that we can always get 259 kilowatts in heating and 169 kilowatts in cooling. And that gives us the temperature profile we saw earlier. So we know we reach the temperature limits, so we cannot install any more power, because we want to be sure that we can use this power over the whole simulation period. But as we saw before, this profile still has potential in heating and cooling in respectively the first and the last years. So that's when we need to go for a methodology that optimizes our borefield for energy. So the objective we want to solve when we optimize for energy is that we want to optimize the energy that we can inject in or extract from the ground during the whole simulation period. So now we're not looking at the power at all times, but we're trying to maximize the energy over the whole simulation period of the borefield. And this means that if we install a certain amount of heating power, we know that we can, during the whole simulation period, be sure that we can get most heating out of the ground. We can extract the most heat out of the ground. But we cannot be sure that we can always get the power from the ground that we have installed. So that's when we end up with the figure like we've discussed before. Now, in order to get there, we have another algorithm. So we again start with our hourly load data and a certain fixed borefield size. And what we do now is we convert this hourly loads to a monthly load, keeping the monthly peak powers and the monthly energy demand equal. And the reason why we do this step is because of computation time. So in theory, you can run this algorithm without step 2, but it will take quite a long time, a couple of hours to even a couple of days. So that's why we converted to a monthly load. And when we've done that, we iterate through every month of the whole simulation period. So if you have 40 years, then we have 48 months. And what we do for every month I is we calculate the monthly temperature profile. So we put our load onto the borefield, we calculate our temperature profile, and we run again the checks as before. So we see if we cross the minimum fluid temperature limit in month I, then we know that the peak power of heating in that month I should be decreased by X%. And the same with the maximum fluid temperature limit. So if we have too much cooling power, we can cross this maximum threshold, and we know that we need to decrease the power in month I by X%. So the main difference with the algorithm before is that we now do this only on a monthly basis. So the third step is, well, if all the fluid temperatures are within the temperature thresholds, then we can go to step 5, which is just go to the next month. When it's the case that in a certain month the temperature limits are crossed, then we reconvert the hourly load to the monthly load, but now we limit the peak power to the power that comes out of step 2. And then we reiterate until we converge and go to the next month. And when we do this for the whole simulation period, we're done and we have optimized our system for energy. So what you can say basically is that the optimization we do for the power, we now do for every individual month within the simulation period. And if we do so, we end up with this temperature profile, for example, where we reach the temperature limits in every year. So we exchange the most heat with the underground as possible. And we know that if we do so, in the first years we can get less cooling than in the later years, and for heating it's the other way around. So that's why we can reinterpret this figure as such, where we say, well, if we have the whole simulation period here, we know that year after year we have less geothermal share in heating. And our peak power drops off and our base load also drops off because of the ground imbalance. So the ground cools down year after year. So year after year we cannot extract that much heat from the ground without crossing the limits. And for cooling it's the other way around. So year after year we see more potential for cooling. We can extract more cooling from the ground. And this gives us an important difference between the optimization for power and the optimization for energy, because since we have installed an amount of power that we cannot use in every year of the simulation, the energy we extract or exchange with the ground differs year after year. So if we optimize for power, we know, well, the power we have installed we can use in every year. So every year we'll have the same geothermal share. In this case, this is not the case, because in the first year we can have more heating share than in the later years, and for cooling it's the other way around. So now not every year is the same after we optimize. So in the end, we have seen the different methods and the different results. If we have the same project with the same hourly load and the same borefield, we can end up with two different designs, so to speak. So if we optimize for power, our 80 boreholes, we see that we can have around 75% of cooling and somewhat more, let's say 80% of heating share from an energy perspective on our geothermal system. But if we optimize the borefield, that same 80 boreholes with the energy optimization algorithm, we can get up to 95% of geothermal share. So that's an important difference. Now, if we take a look at the power, the story is somewhat different. So in this case, we have 169 kilowatts in cooling, 159 kilowatts in heating. And because we know the system is optimized for power, we know we can get this 259 kilowatts and 169 kilowatts in every year of our simulation periods. So this means that if we want to design a hybrid system, that we can be sure we can get this power from our geothermal system, so we just have to install the other building, our required power for the building on our hybrid technology. So there is no system oversizing, which means that this will be the most economical optimization for the borefield if you look at it from an investment point of view. Of course, we leave some energy potential behind, which is rather significant. And that's when we can go to the situation for the optimize for energy. And as you can see here, we install way more power on our borefield. So we more than double the amount of cooling we have on our borefield, and we install our 536 kilowatts also for the heating. But as you can see, the circle is not totally full, and that's because we still have our hybrid system, because we cannot be sure that this power, that we can use it in every year of the simulation period. So if you look at the total installed power, it's bigger than our building, than the power that our building requires. So our total hybrid system is oversized, leading to a bigger investment cost. But on the other hand, since we're exchanging more energy with the ground, probably this system has the lowest operational cost, because geothermal heat pumps and especially passive cooling are a very cheap way to heat and cool your building. So by having more geothermal share in your hybrid system, you can end up with the lowest operational cost. So it's really a matter of optimization between, do we want to have a lower investment cost, or do we want to have a lower operational cost? And that's exactly what we'll be playing around with in part 3. In part 3, we will be jumping over to GHEtool Cloud, and we will see how both methodologies are implemented there and how you can use them for your own project. And we will see that optimizing your borefield for power or for energy are basically two extreme conditions, and your ideal design will be somewhere in between those two boundary conditions. So if you think this video or content is interesting for you, please consider subscribing so you will be notified when part 3 comes out. If it's interesting for colleagues, please share it with them. And I hope I can see you next time. Take care. Bye.